What if I told you that integrating a sum of functions is as simple as integrating each function separately and adding the results? This is the sum rule for integrals, and I'll show you exactly how it works. Welcome to this complete guide on the sum rule for integrals. This fundamental rule in calculus will simplify your integration problems dramatically. The sum rule states that when you have an integral containing multiple functions added together, you can split that single integral into separate integrals for each function. Why does this work? Think of integration as finding the area under a curve. When you add functions together, you're essentially stacking their areas. The total area is simply the sum of individual areas. You'll use the sum rule whenever you encounter an integral with multiple terms being added or subtracted. It's one of the most frequently used integration techniques and forms the foundation for more advanced methods. In the following sections, we'll dive deep into the mathematical foundation, see the step-by-step application process, and work through detailed examples. By the end, you'll master this essential integration technique. Here's the sum rule for integrals in its mathematical form. This elegant formula shows us exactly how to handle integrals of sums. Now let's break down each component of this formula to understand what it really means. We'll start by identifying the left side, the integral of a sum. The left side shows us an integral from a to b of two functions, f of x and g of x, added together inside the integral. Notice how both functions are contained within the same integral. The right side shows us something remarkable. We can split this single integral into two separate integrals, one for each function. Notice something crucial here. The limits of integration, a and b, remain exactly the same for both integrals. This is a key requirement of the sum rule. The sum rule extends beautifully to any finite number of functions. Here's how it looks with multiple functions. This means whether you have 2 functions, 3 functions, or even 10 functions added together, you can always split them into separate integrals and add the results. The key insight is this: integration distributes over addition. Just like you can distribute multiplication over addition in algebra, you can distribute integration over addition in calculus. Remember, this formula is the foundation for solving complex integrals by breaking them into simpler parts. Master this concept, and you'll find integration much more manageable. The sum rule for integrals isn't just a convenient trick. It's built on solid mathematical foundations. Understanding why it works will make you a stronger calculus student. The sum rule is actually a special case of the linearity property of integration. This fundamental property states that integration is linear, meaning it distributes over addition and scalar multiplication. But where does this linearity come from? It all starts with how we define integrals using Riemann sums, the fundamental building blocks of integration. Remember that a definite integral is defined as the limit of Riemann sums. We divide the interval into n rectangles, find their total area, and take the limit as n approaches infinity. Here's a visual representation. Each rectangle approximates the area under the curve. As we use more rectangles, our approximation gets better and approaches the true integral value. Now here's the key insight. When we have a sum of functions, the distributive property of addition over multiplication comes into play. When we sum rectangles for f of x plus g of x, we can separate this into the sum of f rectangles plus the sum of g rectangles. This is just the distributive property in action. The final piece of the puzzle involves limit properties. The limit of a sum equals the sum of the limits, provided both limits exist. This fundamental limit property allows us to separate the limit of our Riemann sums. We can take the limit of each sum separately and then add the results. Now we can put it all together. Starting with our Riemann sum definition, applying the distributive property, and using limit properties, we arrive at the sum rule. Step 1. We start with the definition of the definite integral as a limit of Riemann sums for the sum of 2 functions. Step 2. We apply the distributive property to separate the sum inside the summation symbol. Step 3. We use the limit property that allows us to separate the limit of a sum into the sum of limits. Step 4. Finally, we recognize that each limit of Riemann sums is just the definition of the definite integral, giving us the sum rule. Geometrically, this makes perfect sense. When you have 2 functions added together, the area under their combined curve equals the sum of the areas under each individual curve. The mathematics simply confirms what our intuition tells us. This mathematical foundation shows us that the sum rule isn't just a computational shortcut. It's a natural consequence of how integration is defined and how limits behave. Understanding this foundation will help you tackle more complex integration problems with confidence. The first and most crucial step in applying the sum rule for integrals is learning to identify when an integrand consists of multiple terms that are added or subtracted together. When examining an integral, you need to look for three key characteristics. First, multiple terms connected by plus or minus signs. Second, each individual term must be integrable on the given interval. Third, the terms can be completely different types of functions. Here's our first example, the integral from 0 to 2 of 3x squared plus 2x plus 1 dx. This is a perfect example of a sum that we can identify and separate. We can identify three distinct terms in this integrand. The first term is 3x squared, the second term is 2x, and the third term is the constant 1. Each term is connected by addition signs. Our second example shows mixed function types. The integral from 0 to pi of sine of x plus e to the x plus x squared dx. Notice how we have three completely different types of functions being added together. The beauty of the sum rule is that it works regardless of function type. Here we have a trigonometric function sine of x, an exponential function e to the x, and a polynomial x squared, all being added together. Our third example includes both addition and subtraction. The integral from -1 to 3 of 2x cubed minus 5x plus 7 plus cosine of x dx. Remember that subtraction is just addition of a negative term. We can identify four terms here. The first term is positive 2x cubed. The second term is negative 5x, notice the minus sign. The third term is positive 7, and the fourth term is positive cosine of x. Each term maintains its sign when we separate them. Here are the key points to remember when identifying sums in integrals. Look for plus and minus signs that separate terms. Each term can be a completely different function type. Always maintain the original signs of each term. And finally, verify that each individual term is integrable on the given interval. Congratulations! You have now mastered the first step of applying the sum rule for integrals. You can confidently identify when an integrand consists of multiple terms that can be separated. This foundation will make the next steps much easier to understand and apply. Now that we've identified our sum in the previous step, we move to step 2, separating the integral. This is where we take our single integral containing multiple terms and split it into individual integrals. Here's our original integral from the previous example. We have the integral from 0 to 2 of the sum 3x squared plus 2x plus 1, all with respect to x. The separation process is straightforward. We break this single integral into three separate integrals, one for each term in our sum. Watch as we transform the integral. Notice something crucial here. Each separated integral maintains exactly the same limits of integration. The first integral has limits 0 to 2, the second integral has limits 0 to 2, and the third integral also has limits 0 to 2. This consistency in limits is absolutely essential. When we separate an integral, we must preserve the original limits of integration for every single term. This ensures that we're still calculating the same total area or value. Why does this work? The sum rule for integrals tells us that the integral of a sum equals the sum of the integrals. By separating our terms, we're making each individual integration much simpler to handle. Now each term stands alone as its own integral. The first integral contains only 3x squared, the second contains only 2x, and the third contains only the constant 1. This separation makes applying standard integration techniques much more straightforward in the next step. Remember, the key to successful separation is maintaining those limits of integration. Every separated integral must have the same limits as the original integral. This step transforms one complex integral into several simpler ones, setting us up perfectly for the integration step that follows. Now we reach the heart of the integration process. In step 3, we apply fundamental integration techniques to each separated integral. This is where we use the basic rules of integration that you've learned. Before we integrate our specific terms, let's review the fundamental integration rules we'll be using. The power rule, the constant rule, and the coefficient rule are the foundation of most integration problems. Here are our three separated integrals from the previous step. Now we need to integrate each one individually using the appropriate integration rules. For the first integral, 3x squared, we start by factoring out the coefficient 3 using the coefficient rule. Then we apply the power rule to integrate x squared, which becomes x cubed divided by 3. Notice how the 3's cancel out, giving us x cubed. For the second integral, 2x, we again factor out the coefficient 2. Then we apply the power rule to x, which becomes x squared divided by 2. The coefficient 2 and the denominator 2 cancel out, leaving us with x squared. For the third integral, the integral of 1, we apply the constant rule. The integral of the constant 1 is simply x. This is the most straightforward case and requires no further simplification. Perfect. We have successfully integrated each term using the fundamental integration rules. Notice that each integral maintains the same limits of integration from 0 to 2. The key insight is that each term integrates independently. We simply apply the appropriate rule to each one. In the next step, we'll evaluate these at the limits of integration. Now that we've mastered the sum rule for integrals, let's explore how this powerful mathematical tool applies to real-world problems across different fields. In physics, the sum rule helps us analyze complex motion by breaking it into components. Consider calculating total displacement when an object has multiple velocity components acting simultaneously. If horizontal velocity is 3t and vertical velocity is 2t squared, we can find total displacement by integrating each component separately, then combining the results. In engineering, particularly signal processing, the sum rule allows us to decompose complex signals into simpler frequency components. This is fundamental to analyzing audio, radio, and digital signals. A composite signal might combine a sine wave, cosine wave, and exponential decay. Using the sum rule, we can integrate each component separately to find the total energy or average value. In economics, the sum rule helps break down complex cost structures. Companies can analyze total costs by separating fixed costs, variable costs, and marginal costs, then integrating each component. If fixed costs are constant at 100, variable costs grow as 2q, and marginal costs increase as q squared, we can find total cost over a production range by applying the sum rule. These applications show how the sum rule for integrals is far more than just a mathematical concept. It's a practical tool used across physics, engineering, economics, and many other fields to solve complex real-world problems. Remember, the sum rule states that the integral of a sum equals the sum of the integrals. This simple principle allows us to break complex problems into manageable parts, solve each piece separately, and combine the results. To master the sum rule, practice identifying when integrands can be separated, apply the rule systematically, and always verify your results. The more you practice, the more natural this powerful technique becomes. Thank you for joining me in exploring the sum rule for integrals. If this video helped you understand this important calculus concept, please give it a thumbs up and subscribe for more mathematics tutorials. Leave a comment with questions or topics you'd like me to cover next. Keep practicing, and remember, mathematics is all about breaking complex problems into simpler, manageable pieces.